There's another. There's Dima. Okay, let's. I'm going to talk about this one. So after you do the partial fraction decomposition. So after you do the decomposition, you get this. Pretty ugly fractions, but okay, so this is where we should look at that second integral there. So that first integral, easy, 1/73rd natural log of absolute value of x plus 8. So lots of you are forgetting the absolute values on your natural logs. You're emailing me about these problems. And the reason you're not getting it right is you've just forgotten that you need absolute value. So let's just review it. Just reiterate that. Absolute value, x plus 8. WebWork will count it wrong if you don't have that. But they give you a hint, right? What is it about? It's about domain. So this is good for negative values of x plus 8 and positive values of x plus 8, this original integral. But when you do the natural log of x plus 8, then what goes into natural log has to be positive. But originally in our problem, x plus 8 could have been negative or positive. So that's why we need the absolute value, so that x plus 8 can still be negative or positive, and then what goes into natural log is always positive. That works. Okay, so that's easy. Just don't forget the absolute value. And then now this is, maybe we should go over this. So what we have here is we have negative 1/73x. So what's the overall strategy of this right here? So what's our first step or strategy for starting this? What's that? Okay, but there's something before that. Yeah, we got to split this up. Okay, so what you recognize is that we're going to have this first negative 1/73rd x over x squared plus 9, and then just the constant over x squared plus 9. Okay, and then we're going to deal with those separately. So we've seen that before. Be on the lookout for splitting up a fraction. Okay, so now how do we deal with this? First integral here, negative 1/73rd x over x squared plus 9. So can we just do natural log of x squared plus 9? Can we do natural log of x squared plus 9? Yes or no?
No. Yeah.
Why? Can we? Okay, but that's not why we can do it, all right?
Oh,
so
yeah, yes, we can, because the derivative of x squared plus 9 is x.
Right. The derivative of x squared plus 9 is essentially, it's going to be x to the first, and that's what we have, exactly what we have. If this were any other power, we couldn't do natural log of x squared plus 9, right? So this is set up for undoing the chain rule, because here we have the derivative of this, essentially. So we can do negative 1/73rd natural log of Here we don't need the absolute value because this is always positive, but just always put it on, just to get in the habit. Is this done? What else do we need?
You can multiply by 1/2.
Okay, we need a 1/2. If when we take the derivative of this, we're going to have times 2x, not just times x. So we're going to need another 1/2. Everyone good on that first integral? So we good with that? The only reason we can do that is because it's perfectly set up from doing the chain rule. This is essentially the derivative of that. If this were any other power of x, we could not do this. Okay, now the second one, which you can't even see. It's terrible. The second one is in the room. 8/73 over x squared plus 9. How are we going to handle that? It kind of looks like something that we know. Is it natural log of x squared plus 9? No, because we need an x up here. We can't do natural log of x squared plus 9 without the x that we had over here. So we can't do that. But we should look at this and say it kind of looks like something we know. What does it kind of look like? Arctangent, right? Doesn't it? It kind of looks like arctangent. But why is it not arctangent? Right, our tangent, we need x squared plus 1, and this is x squared plus 9. It absolutely must be a 1. So what we can do is, we can make it a 1, but maintain the whole value of the whole ratio and get that 9 to be a 1. How can we do that? Yeah, so we could, factor out a 9 kind of, factor out a 9, or 1, we can do 1/9, top and bottom. See that? So we can do times 1/9, that's 1/9, and that will make that a 1. But then we've got to change everything else too, so we don't keep the value of the fraction the same. So we've got, on the top now we've got, which I'm not just going to leave it, 8/73 times 9. Just leave it like that. That's fine. And then on the bottom we'll have x squared over 9 plus 1. And what is x squared over 9? That's the same as x over 3 quantity squared. Now we've got arctangents. Arctangent of what? Arctangent of what?
X plus 3.
Yeah, so we got this big constant here, 8. Just hold on to that constant that's multiplied. And then we're going to have arctangent of x over 3. Are we done? So imagine that kind of as a first attempt. If we were to take the derivative of this, would we get exactly that?
No. No, we wouldn't, because
Chain rule, right? Let's do the chain rule. When you do the derivative of this, you'll have it also multiplied by
3.
It's nothing to do with Ellen.
Half multiplied by 3.
Okay, somebody new. So when you take the derivative of this, what will you also have that we don't have up here? Yeah, a 1/3, right? So it's going to be a 1/3 in the chain rule. So therefore, how do we adjust this one? Multiply by 3. So did you catch all that? So first we got to split this up. we take that thing, we split it up into x over x squared plus 9, and then a constant over x squared plus 9. This is undoing the chain rule. Sets up perfectly for that. This one, we can finagle it to be arctangent by making that a 1. But then that makes that x over 3 squared. So it's going to be arctangent of x over 3, which is its own mini undoing the chain rule. We need also a factor of 3, because we don't have the 1/3 that we would get if we took the derivative. Okay. All right, so then the whole thing is this whole result. This one here was this. And then we had this. Which came from here. And then finally we have this. So the second and third came from splitting up that integral right there. Okay, question. Anybody have a question? Like stairs. Good? Yeah, Joel. Yeah, I didn't go over that. I just started right with this part here. So that's the whole that's the whole partial fractions thing, which I didn't do that. I just started with after that. Yeah, well, how would you do these integrals after you got all that? So let's do another one where we'll actually do the partial fractions. Okay? Again, last chance questions on this one. Okay, so let's look at this one. Okay. What do we do first? We got a long divide, right? Because this is greater power than this. So I'll do it fast, but please check, make sure I'm doing it right. So we got x squared, 7x, is 12. X cubed, 0x squared, 0x. Okay, so we got x squared. We need x cubed. So x. Subtract. It's 0. Negative 7x squared. Negative 12x. Please check my work. Bring down 67. We've got x squared. We need minus 7x squared. So minus 7. Minus 49. Minus 84. Subtract. We're going to get plus 37x and plus 151. Is that a remainder? Did I do the math right? This is, we have to minus all this, right? Or minusing all this. Did I do the math right?
Yeah.
Thank you. All right, so then,
One question.
yeah.
When you multiply by 12, you get negative 84, and then 67 minus negative 84.
67 minus negative 84.
Okay.
Yeah. Exactly what you said. Okay. All right, and so then this thing equals what? Our x minus 7 plus the remainder over plus that. So so does that factor? Can we use We need this to be product of factors. Does it factor? Into? All right, let's make this. Oh, do I have sheets? I don't have sheets. 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 Yeah, you guys have just used to say yesterday's? Yeah, just use yesterday's. Anybody still need one that doesn't have yesterday's? Everyone has yesterday's sheet? You lost your clean sheet?
I'm sorry. I totally thought I just forgot to do something on it.
Anyone else need a new one?
Use it for homework.
Okay, so let's have number one be this one. Right there. It's Friday, you can work together, okay? It's Friday, you can work together. I have much higher aspirations for you guys. Okay, can we go on? Yeah. Okay, we gotta go on. You have more time when you're doing other problems to finish that up if you didn't get finished. But so we want to talk about substitutions and change of variables. Substitutions and change of variables. So let's look at this problem right here. So when you look at this, what do you notice? What do you notice? If e to the 2x over e to the 2x plus 3e to the x plus 2. Let's see here.
We can substitute u for e to the x.
And what would the result be?
U squared over u squared plus 3u plus 2.
Yeah, so this is really like a polynomial in disguise, right? This is like a polynomial like the ones we've been dealing with. This is really like something squared plus 3 times something plus 2. Well, that's just a quadratic polynomial, right? And so, but it's all like, instead of, we're used to having just x or some other variable, we've got everything's like e to the x. So what we can do is what's called u substitution. Which you can use anything you want, but like most textbooks, they use u. And so the u substitution we want to do is that u equals what? E to the x. And what we're going to do is we're going to change this whole thing from being in variable x to being in variable u. And let's just say this is from what, 3 to 8, okay? Suppose, okay? Okay, so if that's the case, so we've got dx, we're going to need du. If we're going to change everything into u, then we're going to need what du is. So if u equals e to the x, what is du? E to the x, but by the chain rule, dx, right? So it's like, yeah, so then du is going to be e to the x dx. What about the 2? What about the 2? There is no 2.
Well, why didn't you just replace u with e to the 2x?
Because we're thinking something squared plus 3 times something plus 2. That's going to be our variable, not e to the 2x, right? Okay, so we still don't. We need to find what dx is. So we can use this now, and we say dx equals what? Dx equals du over e to the x. Well, what's e to the x? U. So there's what dx is. Dx is then du over u, because e to the x, that's what we said, it's u. So now we're ready, we can now change this whole thing from x's into u's.
Are you on recording mode?
Yeah. Yeah, so can you see that little red up there? Yeah, if you see that red on right there, then that means I'm recording, but thank you. Okay, so we got e to the 2x. If e to the x is u, what's e to the 2x? So e to the 2x equals what if e to the x equals u?
U squared.
Yeah, that's u squared, right? So e to the 2x is e to the x squared, or e to the x quantity squared, right? So that is. So that's u squared, okay? And so then that's u squared plus 3u plus 2. And then what did we find out dx was? Du over u. And then notice we have u squared up here and a u down here. So u squared divided by u is? All right, are you following everything here? Okay, so now what about, is this still from, any questions on that? So these integrals are the same. They're just, if u equals e to the x, then this is the same as this. But what about this from 3 to 8? Is this still from 3 to 8? Remember these, so this 3 is an x value, right? And this 8, this is, where we're going to start accumulating or start determining this amount of change, and this is where we're going to finish. So is it going to be from 3 to 8?
Yeah. Oh, from 8 to 3.
From 8 to 3. Well, the whole point is we changed from x into u, and what was our definition for changing from x to u? It's this right here, right? So if we start at x equals 3, what does u start at?
Start from 8. Start from
What is it? e cubed, right? So when x is 3, what is u? When x is 3, what is u?
When x is 3.
Yeah, when x is 3,
Oh, u is.
we're changing everything that's x's here into u's.
Then u is e to the 3.
Yes, e to the 3. And so when x is 8, what is u?
E to the 8.
Okay, now what do we have? Undoing the chain rule? Undoing the product rule? What is it? Partial fractions, right? This is partial fractions. We've got, is this, oh, so only if this can be factored. Can this be factored? Into?
U plus 1 and u plus 2. U plus 1 and u plus 2. But what if you can't factor?
If you can't factor that, you can't use partial fractions, right? That was the whole point, that this has to be something that's factorable so that it's the sum of other fractions. If it's not factorable, it's not the sum of other fractions. Okay, and then hopefully this is a piece of cake. Can we do it fast? So it's going to be a over u plus 1 plus b over u plus 2. So we're going to have a plus b equals 1, and 2a plus b equals 0. So this is my u term. So it's going to be au plus bu. And then we have 1u up here, 1. And then 2a plus b equals 0. Subtract. You get negative a equals 1. So a equals negative 1, b equals 1. Did I do the math right? Yeah, I went fast. Yep, I think it's right. No, b is 2. B is 2. Did everything right except the very last step. Is that better? There we go. Okay, so what we have then is and so we get negative natural log of absolute value u plus 1 plus 2 natural log absolute value u plus 2. And we're going to evaluate that from e to the 8. Okay, so another way we could have gone about this. So suppose this was, if this was a indefinite integral, so there wasn't bounds. If there wasn't bounds, then to write your answer, so this is not going to have any use in the end, right? This is just going to be a number, right? When I plug in e to the 8, plug in e to the cubed, and subtract, I'm just going to get a number. And that number is equal to the, what? The total amount, total change of the amount from 3 to 8 when the rate of change is that fraction, okay? But what if that was an indefinite integral? So then our answer, it wouldn't make sense for our answer to be in terms of u, right? If that was an indefinite integral, we would want the antiderivative in terms of x. So how would we get that? We don't want to write the antiderivative in terms of u. We want to write it in terms of x. Yeah, so here's where that all started. U equals e to the x. So this thing is equal to what? Negative ln of e to the x plus 1. Don't erase. Don't erase stuff. Okay, so this is just in case I'm adding to it. I'm not erasing. Right? Plus 2 times natural log of u plus 2, e to the x plus 2. So if it was indefinite, here would be our final antiderivative. Plus c, okay? Or if it's this definite integral, we could evaluate this run from what to what?
Like from 3 to 8.
From 3 to 8, the x coordinates, right? The x coordinates.
If it was indefinite integral.
If it was indefinite, you have to have it back in terms of x. You have to make the substitution. If you undo the substitution after you take the antiderivative. But the way I gave it to you, if you want, you can also evaluate that from 3 to 8, because those are the x values of the bounds. So if you're doing a definite integral, you have your choice. You can change the bounds and stick with the u antiderivative with the changed bounds, or you can forget about changing the bounds and change your antiderivative back to x and then use your x bounds. Does that make sense? Does that make sense? Either way.
Why did dx equal du over u? How did that?
Well, what is e to the x? Did you see that dx was du over e to the x? Did you get that?
Yeah.
Okay, what's e to the x?
Well, I'm saying why is it du over dx?
Okay, because did you see this one? Du equals e to the x dx. So I just solved for dx,
Oh, okay.
which was du over e to the x.
Okay.
Yeah. And then we said, oh, ex is just e to the x is just u. Other questions?
So for definite integral, I'd have to put it with the u, right? I'd have
If it's indefinite,
if it's definite.
definite. If it's definite, you can do either way. You can change your bounds and leave your antiderivative in terms of u, because you're just going to get a number, right? You won't have a u after you evaluate this. Or you can change your antiderivative back to x and use their starting bounds. And that's going to give you a number. It'll give you the same number that you would get here. So when it's definite, it's your choice. You want to change the bounds or you want to change the antiderivative back to x. If it's indefinite, then you have to change it back to x because the original problem is an x. Okay, do another example. Okay, so there's a new skill coming that we haven't kind of embarked on yet that's really important and makes this all a whole lot harder. It's the skill of now you're just given an integral, and you've got all these techniques, and you got not only do you you have to know all those techniques, but you have to know which one applies. Okay? So we kind of go through our list. What's always our first one check? Oh, first one. Undoing chain, right? Undoing chain rule first. Could we undo the chain rule on this one? Yeah, this is pretty ugly, right? This is not going to work for that. Okay? Then there's undoing product rule. We could try, but very unlikely it would work. Okay, and then we've got trig integrals, and now we have partial fractions. So it's not looking like anything. What's that? I'm just going through the list. Yeah, right. It's not trig, exactly. It's not trig. And it's not partial fractions, right? Because it would need to be a rational function with a factorable denominator. Okay, so here's where we could do a substitution and change the variables. So what we could do here is we could substitute u equals this entire argument of the radical here. How do you know to do that? Because it works. So experience and trial and error. Okay. So we could say try u equals x minus 1, but that's not gonna make this any simpler. So what we'd really like is this radical term to be much simpler. So by making this substitution, we're gonna have radical u, and that's something that's gonna be advantageous. Okay, so that's kind of what we're looking ahead towards. Okay, so then we're gonna need dx. So what is du? Du is 1/2. Is that all?
dx over
1/2 times dx over 2?
2. Yes.
No, just dx, right? Okay, so then therefore dx equals?
2 du.
Brock, what does dx equal? 2 du. Okay, now notice that we have this x minus 1. So not only are we're gonna need to know what x is. Okay, what is x in terms of u? So we can get that from this. What is x in terms of u? X equals? So we do a couple steps here. Can we do them all at once? First step is subtract 1. And then after we subtract 1, what would we do? Multiply by 2. Is that fair? Can you see it? Subtract 1, multiply by 2. And that's what x will be. So that's 2u minus 2.
I have a question.
Yeah.
Why is dx and
du over what? Du over 1/2? It's du over 1/2. That's the same as multiplying by 2, right? Okay, so now we're ready to make the substitution. So now we've got x is 2u minus 2. That's x. So then minus 1 is our numerator. And then the denominator is square root of. Okay. And then dx is 2 du. Okay, so we get 2u minus 3 squared over square root of u times 2 du. Did it help? Did the substitution help? Can we see a path here to actually evaluate this integral? Alex, what do you think? Can you see it's a way that's a way forward here?
Where did the two du go?
Let's put the 2 up front, right? Just put the 2 up front. See a path from here? Right? Exactly. Patrick, see anything? Josh?
Not at the moment.
Kieran, see anything? So sometimes you just do the only thing you can do, right? So is there anything you can do? What is it? What can you do? Rectangle. Maybe. That's not the easiest. You're free to do that. It doesn't stop you.
Why I separate them?
What can we do? What can you do?
Oh, first, make two for you squared.
Yeah, just so let's multiply. Can we multiply out the top?
Yeah.
Let's do that. What is it? 4u squared
4u squared
minus 6.
minus 10u.
Or 12. 12 plus 6, not 6.
Plus 9.
Did it help? Tyler, can we do anything from here? Something we've done before. Divide? Like long divide? Not with square root. Well, maybe it depends what you mean. So what do you mean by divide?
I was gonna say long divide. I don't know how to do that.
Make a substitute.
We already substituted. What could you simplify?
Make it 4u 1.5 minus 12 to the 1/2.
3 fractions, right? Split it up into 3 fractions. And then these will each simplify. See it? So what will it be, Tyler?
4u to 1.5
So this is u squared, right?
minus 12 to the 1/2. Of u 1/2. Oh, yeah. And then 9 over the square root.
If you if you want to use fractions, decimals, whatever. 3 halves, 1/2, negative 1/2. See what happened? So by getting this radical as the one term u, then when we get to this fraction now, we can actually split that up and combine u's. So we can just have it u to a power. Okay, so now that should be easy. So it's going to be 8. I guess, do we want to keep the 2 out or do we want to multiply it in? Leave it out? Leave it out. Okay. Good enough. U to the?
2.5.
I should have done fractions. 3 halves, 1/2, negative 1/2. That's what we're used to. When we do these antiderivatives, that's what we're used to. So I should have done that. Okay, so then u to the 5 halves, right? And then 2 fifths. 8/5 minus u to the 3/2, and we'll need 2/3. 2/3 of 12 is 8. U to the 1/2. We'll need a factor of 2, so it'll be 18. Are we done? What's that? Are we done? Is this our answer? Joel? Yeah, tell me, what will it be? Can you tell me, Joel?
So should be 8 this. One half x plus 1 to the 5
Good, keep going.
minus 8 to the 1/2 x plus 1.
Not to the times.
Times this.
Yeah. To the 3/2. Okay.
Plus 18 times 1/2 x plus 1 to the 1/2.
No, it's positive, sorry.
Oh, yeah, that's fine.
You're right, you're right. Sorry, can you do that? 1/2, 18, 1/2 x plus 1 and 1/2. Did you catch it? Does this make sense? So indefinite integral, gotta be in terms of x in the end. So we gotta go back and back substitute our 1/2 x plus 1 in for every u. Any questions on that one? Okay. So for your sheets, no, this won't work. Just x. So x times the cube root of x minus 2. Yeah. We're gonna 11:15. We're gonna move on here. So we got 1 minute. Okay, we're gonna move on.
I don't know, this is two items we have, this one here, and this one.
Doesn't take it off.
Yeah.
Oh, yeah, I'm sorry.
Because
So,
they equal each other.
Yeah, I just put one.
Okay, so another type of substitution is what's called trig substitutions. So trig substitutions are based on right triangles. So the x in the integral will be one. We're going to make that one side of the right triangle. For instance, let's just put it here. Okay, and then the other side of the right triangle could be some constant given in the problem, like 2 or 4 or 5 or 3. We'll call it a. Okay. So then, in that case, then what is the length of the hypotenuse? So I've got x is this leg, and then a is this leg. So x is our variable of the integral, and a is some constant, is some number. What is the length of the hypotenuse then in that case?
The root of a squared plus x squared.
Yep. Right? So then for this triangle then, we could change from variable x to variable theta by using our trig ratios. So we've got what? Sine, cosine, tangent, secant, cosecant, cotangent. Let's write all those out. So for this particular triangle that I drew, so this would be triangle number 1. So this is triangle number 1. We're going to do another triangle in a second. So we'll kind of make a table, okay? And we'll do triangle number 2 in a second. So for triangle number 1, can you write out what sine theta, cosine theta, tangent theta, secant, etc., cosecant, cotangent, what they all equal? Do you know? Do you remember? What would sine theta equal? Who remembers? Joel?
1. It's going to be x over the root of a squared plus.
Yeah, sine is opposite over hypotenuse. So hopefully you guys were all thinking x over square root of a squared plus x squared. It's a square. Cosine. A. Tangent. Opposite over adjacent. Secant. So secant is just 1 over cosine, right? Secant is 1 over cosine. So what would happen if we did 1 over that?
Root of a, that's
Yeah, just reciprocal, right? 1 over is reciprocal. Or hypotenuse over adjacent. Cosecant is 1 over sine. So it's hypotenuse over opposite. And then cotangent,
a over x.
A over x. 1 over tangent or adjacent over opposite. Okay, but suppose that, what if our variable x was the hypotenuse? and then just to change things up, this opposite leg is A. Then what would the adjacent side be? So this is triangle 2.
Root of x squared minus a squared.
Square root of?
X squared minus a squared.
And now for triangle 2, we could write out all these same ratios again. We're not going to take the time because we want to get to an example, but let's just talk them through. Sine theta would be, what would sine theta be?
X.
Drop A over x. What would tangent be? Patrick, what would tangent be in the second?
Square root of x squared minus a squared over x.
Square root of x
Sorry,
squared
oh, tangent, sorry.
tangent.
That would be a over x. A over the square root x squared minus.
Right, it would be a over square root of x squared minus. And what would cosecant be? Shana. What would cosecant be in the second triangle?
X over a.
Well, Shana, your voice changed. Got deeper. X over square root of x squared minus a squared would be cosecant. What is cosecant? Cosecant is 1 over sine. No. What is sine? Sine is opposite over hypotenuse. So cosecant would be opposite, should be hypotenuse over opposite. One more try. That's sine. Sine is opposite over hypotenuse. Cosecant would be hypotenuse over opposite. X over A. So the idea is that we're gonna get some integral, and it's gonna have an expression that's made up of these kinds of things: square root of a squared plus x squared, or square root of x squared minus a squared, or even it could be square root of a squared minus x squared. That would be if the hypotenuse was what? So if we get an expression like square root of a squared, a constant squared minus x squared, then our triangle has a hypotenuse of length 1. Not 1.
Is that triangle 1?
It's a different triangle. It's a new triangle. It's a third triangle.
Wait, could you say?
So I'm gonna have an expression that says square root of a squared minus x squared, and that's gonna relate to a triangle. What will the hypotenuse, the length of the hypotenuse be in that triangle? It'll be a, right? It'll be a.
How is that?
How is that? Because one of the legs will be square root of a squared minus x squared. So the only way to make this work is that the other leg is what, and the hypotenuse is what? The other leg would have to be x, and the hypotenuse would have to be. This is the only way it works. It's the only way it works. That triangle. Okay. All right, so let's try an example here. So basically, it's going to be a change of variables from expressions like these, or combinations, or variations on expressions like these, and then we're going to change variables into theta, and then we're going to have a trig integral to do. We're going to use trig integral to solve it, okay? And then we switch back from theta back into x's, like we did before. So let's just try here, x squared over. So what's cluing us, so these are sides, so we see this, we see these are sides of a right triangle. So is this a leg or the hypotenuse? Why is it hypotenuse?
Because
You should know. You should know why.
Because
Tyler.
because it's a constant minus. Because same situation we just had.
I don't see minus. I don't see minus. There's no minus. Is this a leg or hypotenuse?
That's the hypotenuse because of the class between.
It's because it's plus, right? It's because it's plus. The hypotenuse would be the square root of a squared plus b squared, right? So that has to be the hypotenuse. Does that make sense? And so then what are our legs?
2 and x.
2 and x. Take your pick. Doesn't matter. You can put the 2 here or you can put it up here. But we'll just do it this way. 2 and x. Okay, so now we need what x is, or x squared. And so what relationship is going to get us this x? Well, it's going to be, certainly we want this opposite side. And then do we want the hypotenuse along with that, or do we want this adjacent side? If we just want to try to figure out what x squared is. Yeah, we want to use the adjacent side. We don't want to get this involved, right? If we're trying to solve for x squared, then constants are fine. So we have tangent of theta equals x over 2, and therefore x equals 2 tangent theta. And so then our x squared will be, so now we've got it, right? X squared will be 4 tangent squared theta. And then what about the square root of 4 plus x squared? We need to associate that with another side to do one of these ratios. Do we want to do opposite or adjacent? We don't want to involve another x, right? Constants are what we love. They're our friends, right? They're easy. So we want to associate this with a constant. So we want which relationship there? We've got adjacent and hypotenuse is cosine. So we want cosine theta equals 2 over so therefore square root of 4 plus x squared equals 2 over cosine. And then finally we're going to need what dx is. How are we going to get dx? We're going to get it right from here, right? So dx is what? 2 secant squared theta d theta. Because the derivative of tangent theta is secant squared. So now we're ready to go. We're ready to plug everything in. X squared is 4 tangent squared. Square root of 4 plus x squared is 2 over cosine theta. Dx is 2 secant squared theta d theta. And now we can use identities to get this as simple as we can. So first of all, we got a 2 and a 2 that can go away. Let's take those out. Okay, and so what do we got? 4. So what is tangent squared? That's sine squared over cosine squared. Let's just get everything in sines and cosines, so everything cancels out. Then times, this is 1 over cosine in the denominator, so that's times a cosine. And then secant squared is 1 over cosine squared. So, in the end, what do we have? 4. How many cosines do we have? 3 in the denominator. Tangent squared is sine squared over cosine squared.
Yeah, so
Here's our tangent squared.
3 cosines.
There's 3 cosines in the denominator. 3 cosines in the denominator. So the next thing to do, evaluate trig integral, then back substitute for x. Using the ratios. Does the general idea make sense? You're gonna, when you see these are sides of a right triangle. Set up your right triangle so that it works, and you're gonna use your trig ratios so that you can substitute in trig ratios and change it from x into theta. And then you'll have a trig integral that we did a couple days ago. Evaluate the trig integral, and then back substitute for x.